Hello again, Math 410 class. Today, in this video, we're going to talk about what happens when you have complex roots of your characteristic polynomial. And so here, we saw in the last videos that if our differential equation looks like this, its characteristic equation becomes ar squared plus br plus c. And let's now suppose that those roots that we get are complex conjugate roots, so alpha plus or minus I beta. This should be somewhat familiar since we've dealt with complex roots of characteristic polynomials in the past. And so now what we do is we take the roots, and those are the exponents multiplied by t of e, right? So we get, and I'll use the letter k since we'll get to the letter c later on. But we get k1 e to the first root times t plus k2 e to the second root times t. Okay, so here's how we're going to get rid of the letter I, right? So first thing we're going to do is we're going to recall Euler's formula, which is e to the I theta equals cos theta plus I sine theta. And so now what that allows us to do is to rewrite x in terms of sines and cosines. So what we're going to get here is we're going to get x equals k1 e to the alpha t times cos beta t plus I sine beta t plus k2 e to the alpha t. And now technically what we get is cos minus beta t, but cos is an even function, so minus beta t is just the same as beta t. And we would then get plus I times sine negative beta t, but sine is odd, so that negative actually can move out, and you get minus I sine beta t. And now if you combine the like terms, so the things with cosine and the things with sine separately, what you get is you get k1 plus k2 e to the alpha t cos beta t plus I k1 minus k2 e to the alpha t sine beta t. And so what we're going to do is we're going to redefine k1 plus k2 to be a new constant called d1, and k1 minus k2 to be another constant called d2. We're going to get x equals d1 e to the alpha t cos beta t plus I d2 e to the alpha t sine beta t. And the observation, just like from Unit 2, is going to be that e to the alpha t cos beta t and e to the alpha t sine beta t are going to be, in fact, real valued solutions that are also going to be linearly independent. And so our x1 is going to be e to the alpha t cos beta t, and our x2 is going to be e to the alpha t sine beta t. And so we notice that I is now gone, and so if we want just the answer to a problem with complex roots alpha plus or minus I times beta, then it's just going to be x equals c1 e to the alpha t cos beta t plus c2 e to the alpha t sine beta t. All right, so moving to the next page, we have some examples now. So let's go through these. We see here we have y double prime plus 25y equals 0. So that corresponds to a characteristic equation of r squared plus 25 equals 0. And that tells us that r is plus or minus 5i. I'll let you verify that. And so that tells us now that y equals c1. Well, there's no real part, so it's e to the 0t, which is just 1. So we just get c1 cos 5t plus c2 sine 5t. And you'll notice that just like the last videos, we're going to need y prime, so we better find that now. It looks like we're going to get minus 5 c1 sine 5t plus 5 c2 cos 5t. And so putting this together, you'll notice that 6 is what I get when I plug 0 in for t in the function y. So that's just c1. Oh, that was easy. And minus 10 is what I get when I plug in 0 here, and that is 5c2. And so that tells me that c2 equals minus 2. And so at long last, the answer is y equals 6 cos 5t minus 2 sine 5t. All right, moving to the next example. The characteristic polynomial is going to be 2r squared plus 1r plus 1 equals 0. And if you work, the roots are going to be minus 1/4 plus or minus I root 7 over 4. Just use quadratic formula for that. And so that tells me then that y is going to be c1 e to the minus 1/4 t cos root 7 over 4t plus c2 e to the minus 1/4 t sine root 7 over 4t. And now your job would be to find y prime as well. I'll just give you the final answer, but you're going to need to do product rule on each of these. So we get minus 1/4 c1 cos root 7 over 4t minus root 7 over 4 c1 e to the minus 1/4 t sine root 7 over 4t minus 1/4 c2 e to the minus 1/4 t sine root 7 over 4t plus root 7 over 4 c2 e to the minus 1/4 t cos root 7 over 4t. And so now what you would do is plug in 0 into y, and that will give you 1. So it looks like 1 equals c1. And then you would plug 0 in to y prime, and that's supposed to give you minus 2. That's minus 1/4 times c1, which is just 1, plus root 7 over 4 c2. And that tells me that c2 then has to equal minus root 7. I'll let you verify that. And so y is therefore, c1 is just 1, so it's e to the minus 1/4 t cos root 7 over 4t minus root 7 e to the minus 1/4 t sine root 7 over 4t. All right, and the final example for this video coming down here. I think our characteristic polynomial is going to be r squared minus 6r plus 13 equals 0, the roots of which are going to be 3 plus or minus 2i. I'll let you verify that using quadratic formula. So x is going to be c1 e to the 3t cos 2t plus c2 e to the 3t sine 2t. I'll let you find x prime, but I'll tell you right now that c1 is going to be 0. You would do that by first finding x prime and then using the initial data here. c1 is going to be 0 and c2 is going to be 5. And so what that leaves us is just x equals, well, 0 multiplied here. We'll just erase all of that. And so you just get 5 e to the 3t sine 2t. In the next and final video for Unit 3.1, we'll go over the last two pages, pages 8 and 9.